Well, the basic building block that we use here, and that both Carl and I had extensive knowledge of, is composition modified barium titanate powder. Well known that those powders have the highest permittivity of any materials in the world, although they had some very significant problems, and people tried for about 30, 35, 40 years to solve those problems by varieties of techniques, processing, and that stuff. But classically, they never really took the full approach that we did to attack those problems on an individual basis as we go through a production process. We saw in the past what they did. They would take these constituents, barium, titanium, calcium, neodymium, manganese, yttrium, lanthanum, zinc, tin. They put those into a ball milling system and ball mill these powders down so they get it into a reasonable size. Then they would take and calcine those, and they would grow together, very high temperatures. Then they'd calcine them again, but they'd ball mill them again. They kept that process up until they got something that was halfway decent, but still a long, long way from optimal. In looking with that process, if you make capacitors out of those materials, and this is where the guys in the industry, they say, well, the voltage is such a deep problem. Well, it was for them. For after all, they did not take the time to really solve the technical problems properly, and therefore you apply a voltage to those type of powders, and they lose permittivity over time. And also, if you have a very high voltage, you get what's called domain wall slippage, and you lose all the permittivity. So those are some nasty problems that had to be overcome if one is going to work with barium titanate, composition modified barium titanate powders. Well, the first thing we concluded that there's no way you'd ever make this work using ball milling. So we said we would use our experience in chemistry and make this a full aqueous process. And the reason you can do that is that you can get these materials all in a nitrate form, and nitrates are water soluble, but you can't blend them together. If you did that, a lot of them would just plain fall out, and you couldn't get a good blend. So we had to invent some chemistry so that we could pull off this aqueous process. That took us about a year of work there, of really going through and getting the chemistry optimized so we could blend this stuff together and get the proper constituents that we're looking for. Well, we're happy to say that that succeeded, and we've done a great job because a lot of this stuff has been out here over 3 years, 3.5 years, and no degradation whatsoever. I mean zero, nada. So we're very happy that we really have superior chemistry here from the aqueous process. Then we went into a very detailed purification process. The two ions that are very detrimental to getting the high voltage is sodium and potassium. Like if you put salt inside of water, the resistance of the water goes down because you've got 3 ions in there. But we worked hard to invent processes where we could purify all of our activating chemistry and also the coating process that we put on these powders. And the reason we coated the powders, just to back up a little bit, with aluminum oxide, which is the highest resistivity material in the world and the best seal in the world, because when you add voltage to these materials, you lose oxygen if you coat the particle, as it states in our patent. So this is all public domain information. You kill the loss of oxygen, which totally shuts down the problem of putting voltage onto these products and losing permittivity. So that was a big breakdown. And Carl and I have used aluminum oxide before for in the integrated circuit world for the same reason. So we have a lot of experience in that. Coating the powders took a patent process which we have working out here, so we can coat the powders very accurately. And so we know how to put that. We know how to put those powders on particle on each particle and keep it down to 100 angstroms plus or minus very few angstroms. We know how to put it on very accurately. Again, one of our patented processes. So we got going on the purification, got that going, and that took us about 6 to 8 months. So that was into the second year. And then we certified that when we were done with Southwest Research down there. Anything we do, any news releases, we always get it certified, no hype. Mm-hmm. And Southwest Research, one of the most sophisticated chemical analysis companies in the world. And we sent it to them, they analyzed it, and our particles purity was in the range of parts per million. And then through a little bit of work on aluminum nitrate and a few other things, we got it down to parts per billion. Now, if you take and purify our stuff down to that level, and we got a certification on that, we mentioned in one of our news releases. If you certify, let's take the aluminum oxide, and you certify it down to that level, the voltage breakdown on the aluminum oxide, certified die, mind you, and it's in our news release, gets to 1100 volts per micron. We're at 350 volts per micron on our working voltage, and you can see we're more than 3 times away from our working voltage, which is more than enough for safety of that type of activity for voltage breakdown versus the working voltage. Usually 1.5 is more than enough. Where we see we're actually 3, a little better than 3. So there's no real heartburn there of getting our voltage. Now, another thing on voltage, and I did put that in another news release, is that we work deep into the paraelectric phase. In the paraelectric phase, we have very sophisticated test data certified that in the paraelectric phase, there are no domains. And this is where the people, the bloggers out there, well, my God, you're going to just lose your permittivity with voltage. Well, you would if we were in the paraelectric phase. In the ferroelectric phase. Barium titanate, composite barium titanate is a 2-phase material. It's barium. It has a paraelectric phase and a ferroelectric phase. Now, all the colleges and universities and all those PhD guys out there are very familiar with the ferroelectric phase. If you apply voltage to it, you get to a voltage, you have the main wall slippage, and you lose your permittivity. It's not true if you're in the paraelectric phase, and I pointed it out very clearly in one of our news releases. If you're in the paraelectric phase, it's very difficult to get polarization saturation because your dipoles shift. They're now electron clouds, and you can expand them. And on top of not only that, we have a patent pending process, where we can polarize our dipoles so they all shift through 45 degrees. That means our polarization saturation has been improved by at least a factor of 4. Well, you see that that's now taken that out of a non-problem now. So not only got the voltage breakdown under control, like the polarization out of control, we've got the purification behind us, the chemical saturation, the chemical stability is more than proven for a 3-year period, and all those chemicals in the last minutes in the factory, you're going to go through that quick. But we got it where it's lasting for 3 years. Once you get all this done, now you've got it where your chemistry and all that stuff, but now you need to, after you blend this stuff, you have to take that blended chemistry with your constituents in there, and you have to produce powders out of it. And the technique that we use there, which is all this, by the way, this is all unique. No, there's no books on this. You take that and you put an activating chemical with that using a very particular set of processes, and you produce powders. When you do that, you can set the powder size to be in the neighborhood of 0.65, which we did. And when you do that, you get exactly the size of a crystallite, but they won't talk to each other. Then when you coat them, you've now sealed in all the goodness. All that's behind us now, and all that is working, and all of our high technology has been completed up to that point and then beyond it. The last thing we had to invent was a decomposition and calcining phase, where you now have to take your powders and remove the activating chemistry without destroying your chemical structure, and then you take it up to a calcining temperature, and you calcine it where you densify it up to the 99.99% level. In other words, highly densify it. We're happy to say that when we did that, we showed through what they call drift FCR, very sophisticated drift FCR analysis, and quantitative X-ray diffraction, that we truly had hit the home run, because now all the activated chemicals down to parts per trillion, you couldn't find it. So we totally removed it, and our decomposition calcining phase produced powders that had perfect cubic perovskite structure. That means you're deep into the paraelectric phase. Okay, we knew we'd hit the home run then. Then we took care of a few other processes for agglomeration that time. Then we started making powders. When we made the powders, we were very happy to see that we truly did hit the home run, and the permittivity was 22,500 and or higher. So we didn't want to tell the world exactly what we got. We told that to Zen. Zen hired a company over here called PTI, a professional testing organization, and a gentleman named Dr. Gola, who's also worked for Texas Research International, and they worked for Zen Motors and came into our factory after they signed on to the agreement, and they ran the test for the permittivity certification. We're happy to say it passed the test with flying colors. We told the world 18,500, and our test shows that it's 22,500 and greater. We're just not going to tell how great it is, but there it is. So we've passed all those milestones, and when we passed that technology there, we've been going very hard. Now, Zen made a payment for the $700,000. We took that, and we're putting it again to very good use. We've got equipment out here. We're actually installing our stuff now to go into EESU production, and we've told the world that you can anticipate us being in a pre-production mode of EESUs by the fourth quarter this year. Here it is June, and I'm already putting the systems together. So it looks like I'm ahead of schedule. So the things are happening very quickly.
How much of this material have you produced?
We tens of thousands of grams of it per time. So a huge amount. It's all automated, by the way. Remember, what I'm putting in, what I got funded for by kind of first call from the buyers was not to do R&D, although we finished R&D, was to put in a full production line, and that's what we got here. We're 85% complete on our first production line, which is a modular concept. And so when this is done, it is full production, so I can actually press buttons now and produce powders. So all that has been automated, and all the automatic controls in there for all the chemistry has been complete. Then I'll be putting in controls now in automation, which are mainly pick-and-place robots for taking the components and making ESUs with them. We'll put that automation, though, probably in the first quarter of next year. If we get everything going, we can make it work very nicely, get some pre-production units out of here for testing and for our customers to build product out of.
Okay, and then when you talk about going into the ESU production, what are some of the key issues in going from the material into more of a product prototype?
Well, the key thing is what we've got is the thing is, can you get the hardware quick enough to actually ramp up and put your lines in a very effective time frame? We're happy to say that all of our suppliers are U.S.-based. I got one Canadian supplier doing a great job, or North American-based then. And they all can produce the stuff in a very timely fashion. It's more off-the-shelf type things. So I'm not asking for some, $5 million